All right, good evening, all. This is Mr. McKeever coming to you from my wonderful abode yet again. Recording the first lesson for physics. Congratulations, you've made it through your math portion of this class. We are now moving on to the science portion, which involves dealing with physics. Now, this is usually the part where people start freaking out because physics, some reason, scares people. I will do my best in this class to make sure that physics for you is not only something you potentially enjoy, but you can see how it applies to physical therapy, because in physical therapy, we have physics, right? Our whole profession is based upon the math and science of physics. It just is. There's tons of things that we're going to talk about, from something as simple as simple machines to the way the body works. It's all physics related. So it's important to understand the basics of physics. So when we talk about stuff in kinesiology, like the pulley system of the neck or the pulley systems of the knee, that you understand the forces that are interacting there. Or when you have a patient that tears their quad, you understand why that quad tear occurred. Or when you have somebody that's got a disability dealing with an imbalance of muscles, that you understand how that imbalance of muscle plays out and how to adjust the physics of those forces to overcome that. So that's kind of the point of physics, right? We're going to get into that here just as we go through. So we're going to talk about the physics and science. We're going to talk about some force. We're going to talk about mechanical and also dynamic equilibrium. We're going to talk about some vectors. So Lord Kelvin, who is kind of the guy that designed the Kelvin scale for measuring temperature and actually energy transfer, came out with a pretty famous science phrase. It says, I often say that when you measure something and express it in numbers, you know something about it. When you cannot measure it, you cannot express it in numbers, your knowledge is meager and unsatisfactory in kind. It may be the beginning of knowledge, but you've scarcely in your thoughts the advanced stages of science, whatever it may be. Basically saying, if we can't measure, quantify, and collect information on something, how can we ever really understand it? Right? That's kind of the thought process behind this. So Earth, right? We can't control the Earth's motion, but we understand how it moves. There's a great quote in one of the Justice League movies that to this day just makes me crack up every time I think about it. When it's in Justice League Doom, okay, you guys know I'm a total comic book geek, so just bear with me on this, that the Earth is actually being attacked by a huge set of solar rays coming from the sun. And Superman suggests, well, maybe I can just move the Earth out of the way. And Batman, in his best quib, comes back with, even if I had a week, I couldn't explain to you all the ways that wouldn't work. Exactly. We can't control the Earth's motion. We've learned what rules by which it moves. We understand how it moves, right? We understand where it is in space. We understand how it goes around the sun. But that took eons to study, right? So when we look at nature's rules, it's kind of what physics is about. It's understanding the rules, and it adds richness to the way we see our world, and also adds richness to our practice. Physics is about the nature of basic things: motion, forces, energy, matter, heat, sound, light, composition of atoms. It's kind of the most basic form of science, right? The study of science branches into all kinds of studying things, right? Living and non-living. So we have life sciences like biology, zoology, botany, and then we have physical sciences, right? Like geology, astronomy, chemistry, physics. You know, we talk often that geology is a great science because it rocks. But you can understand all those sciences if you first understand physics, right? Which is why a lot of times when you're taking any type of advanced degree, one of the things they require is for you to take 2 courses of physics. If you were to go on for your DPT after you're getting your PTA, one of the prerequisites for almost every single DPT program out there is 2 courses of physics. It also usually requires a chem and an organic chem, but we'll talk about that when we get to the chemistry of atoms and stuff like that. But physics is the most basic of all sciences. Then we talk about chemistry. It's how the matter is put together. If we don't have physics, we don't have chemistry. If we don't have the forces holding the atom together, we don't have the atom, so therefore we don't have chemistry. And then if we don't have the atom, then we don't have compound structures, we don't have compound materials, and we don't build up the body. Therefore, we don't have biology. And then we get to mathematics, because we just went over math in this course, but mathematics in itself is really the way that science is expressed, right? Math is an unambiguous term. It is or it isn't, right? 1 + 1 is 2. The equations of science provide compact expressions of relations between concepts, right? And the methods of mathematics and experimentation lead to enormous expansions in science, right? Think about it. I've got my phone here. Back when I was in you guys' shoes, way back when dinosaurs roamed the earth, our phones were these huge bag devices. And, you know, most of the time, unless you were in the major city or around a major city, that phone didn't work, right? If you weren't around somewhere that had great low band cellular service, the phone didn't work. You could be out in the, where I'm from, out in the boonies, and you didn't get a signal out there, right? But you went close to Harrisburg, close to Philadelphia, yeah, your cell phone worked. Now we have one of these things, and pretty much anywhere in the world, we can get a signal for the most part, right? Or at least GPS to know where we are. And how do we know that? Well, mathematics has helped us develop this. Physics has helped us develop these phones so that we can text somebody at 3 o'clock in the morning and ask them, what's up? So this is a comment. I love this phrase because I've had a lot of my friends, I'm going to use friends loosely. A lot of people where I'm from say, well, that's only a theory, right? And what is a theory? Well, is it a guess? No. Is it a number of facts? Yeah. Is it a hypothesis? Yeah. It's more like a vast synthesis of well-tested hypotheses and facts. So a hypothesis we're going to talk about is a guess, but it's supported by facts, right? Yeah, it may only be a theory, but there is evidence behind that theory, right? So the word in theory in everyday speech is different than it's in science, right? I hate when people say, oh, science is a theory. Gravity is only a theory. Yeah, because we've proven it, right? Earth is round. Oh, it's only a theory. No, the earth is round. Sorry. I'm just going to say it. There's no such thing as flat earth. We'll get into that later. But the world theory just kind of defines that we have this well-defined wealth of knowledge that shows that it is what it is, right? Science is a vastly experimental, verifiable knowledge, right? That's a background. When we have a theory, it's important. That means we've researched it. It's not a guess, right? We don't guess why gravity pulls down. We understand that gravity is being pulled down because of the mass of the Earth, the inner spin of the core, right? What the core is made of, the magma of the core, everything like that. We have scientific evidence that shows us why this happens. The scientific method generally includes some, if not all these, right? We recognize a problem. So let's look at our science right now. We recognize a problem that's going on in the environment right now. We have COVID-19. We have to make an educated guess. And we did initially. We made an educated guess that COVID-19 was a droplet disease, meaning that it only spreads by large drops. So based upon the consequences of that drop, only the people that are in close contact with each other for long periods of time are going to get sick. Well, we performed unfortunate experiments on this, right? Because people didn't listen to the science and they got sick. So we had to go back and go, that educated guess was wrong. We had to form a new guess. Maybe this is airborne. And now we're finding out it is, right? So we form these general simplest rules and we come up with hypothesis, prediction, and experimental outcome, and then we test it. And we test it incessantly, right? The scientific inquiry attitude is one of inquiry, experimentation, and willingness to admit error. One of the biggest problems, one of the things that bugs me right now, and if you're listening to this in the future, it's going to be a problem then, is our government says, you know, Dr. Fauci, who's one of the top leading immunologists in the country, said, at first, we don't need to wear masks, right? He said that. Well, there's a couple reasons for that. We're not even going to get into the reasons to protect medical professionals. But he then realized in the third problem here, the willingness to admit error. It was wrong. It's not a droplet precaution virus. It is airborne. So he was willing to admit that he was wrong, do some more inquiry, do some more experimentation, and come out with some new facts, right? Facts change based upon the information we are given and the study based upon them. So they're extremely effective in gaining, organizing, and applying new knowledge, right? Scientific methods either credited to Galileo, right? Or it's credited to Francis Bacon. They both had some hands in this. A lot of the research you look in says that Galileo developed and Bacon then further refined it. But we can all deal with a little bit of Bacon in our life, right? And though the method is popular, it's not the universal key to discoveries, right? And advances in science. Sometimes trial and error happens. Experimentation without guessing, accidental discovery. Some of that happens, right? We didn't know we have some of the species that are out there until we come across them. We weren't looking for them, right? Sea snakes are a great example of it. We weren't looking for sea snakes, right? When we found them, we didn't even have a scientific hypothesis they existed. But then in deep sea dives, we found them, and the deep sea worms, right? Science has more to do with the attitude of inquiry and the questionness of experimentation and the humility to say, I may have been wrong. Now this is what I found out. Same thing's going to happen in physical therapy. We've got to constantly adapt in physical therapy. Maybe this isn't the best treatment for this condition. We have to be able to adapt and overcome. If a scientist finds evidence that contradicts his hypothesis, law, or principle, then the hypothesis, law, or principle must be changed or abandoned, right? If tomorrow we found out evidence that 1 + 1 = 3, and we have good, solid, verifiable evidence, we have to throw out our previous knowledge, right? Or research it further to determine if the new knowledge is in fact valid. So fact itself is a close agreement by competent observers, scientists, who make a series of observations of the same phenomena and come to conclusions, right? Based upon scientific hypotheses. And those are educated guesses that's not fully accepted until demonstrated by an experiment. In order to have a valid scientific hypothesis, there has to be a test to prove it wrong, right? I can't just say, you know, if I made a hypothesis and said, well, that the New England Patriots are the worst football team ever in the NFL, there's not a valid test to prove that wrong. That's the problem. I mean, there are hundreds of variables that we could take into what's considered best, right? Could I make a scientific hypothesis about a specific quarterback having the best quarterback rating ever in a single season? Sure, I absolutely could. I know I'm taking a sports analogy here, but bear with me a bit. Because there is a verifiable set of numbers that is the quarterback rating. We can go back historically and look at those quarterback ratings, and we can prove that test right or wrong, right? When hypotheses about a relationship among natural quantities are tested, repeated, and not contradicted, they will then become laws or principles. So here's the deal. Scientists must accept their findings even when they don't want them to be, right? I'm going to talk about blood flow a little bit, or blood flow restriction, when we go through this course and a couple other courses. Because one of the things about blood flow restriction, if you go out and you look at the wealth of scientific data on blood flow restriction, there is no scientific data that says blood flow restriction is bad. There's no negative effects from blood flow restriction that's ever been researched in physical therapy. That's my concern. Why? Well, because the scientists that are researching blood flow restriction have a vested interest in showing that it works. So they've been consciously ignoring the negative effects of blood flow restriction. Does that mean blood flow restriction doesn't work? No, absolutely. For certain clientele, it works fantastic, but it doesn't work for everybody. It's not a universal fix-all for all people, right? So that's the thing, is we have to be able to accept findings, even if they don't necessarily support what we want, right? Scientific theory is a synthesis of large body of information. The more information we have, the more well we test things, the better that theory becomes. And that theory of science evolves, right? We used to think about it way back when the earth was flat. We know the earth is round. We used to think the earth was smaller than the moon. We now know that's not right. We used to think the earth was larger than the sun. We now know that's not right. We used to think the sun revolved around the earth. We now know that's not right, right? So we evolve as time goes on. The refinement of theories is a strength of science, not a weakness. People try to use it as a weakness. Say, well, you know, you're still testing these things. Yes, that's what science does. Science tests. And more important than defending beliefs is improving upon them. You know, we look at going, okay, well, we tested masks and shown that masks are effective against transmission of coronavirus. But then we went further and tested and go, well, this type of mask isn't effective. Those with valves on them, not effective. Single layer cloth mask, not effective. Bandanas, effective to a point, but not as effective as maybe a triple layer or a double layer mask, right? Not as effective as an N95 for sure. So it's better to keep improving upon those ideas. That's the scientific method, right? Better hypotheses are made by those who are honest in the face of experimental evidence. I go back to this blood flow restriction case, right? If we had scientists that are studying, or physical therapists, PTs, PTAs, whatever it is, studying blood flow restriction are willing to say, well, blood flow restriction doesn't work for this matter, and then proves that it is, that actually is a little bit more honest than just saying blood flow restriction works for everything, right? I'm gonna beat on that just because that's an easy target right now. Doesn't mean in the future it might not be. In the future, we may have a wealth of evidence that shows what it's good for and what it's not good for. At that point, great. Then we have a wealth of evidence. Right now, we don't. Hypothesis must be testable. It's important there's a way to prove it wrong. The atom, right? We used to think that protons, neutrons, and electrons were the smallest parts of an atom. We now know there are neutrinos and other things out there that are smaller. Well, how do we know that? Well, we had proved that. We said, okay, well, maybe the electron is the smallest part of an atom. We researched and found out, no, that's not right. Then we found out this other stuff. No, well, maybe that's the smallest part of the atom. Well, no, maybe we found out. And so if there's no test to prove something wrong, it's not scientific. Experiment is the test of truth in science, right? Here's a hypothesis that's not scientific. No material object can travel faster than light. Well, why is this not scientific? Well, because we haven't been able to approach faster than light speeds yet. Could it be scientific in the future? Absolutely. We may be able to prove that a material object can't travel faster than light, right? FTL is the big term you hear a lot of times in all the sci-fi shows, right? FTL or warp in Star Trek, right? Light speed in Star Wars. FTL drives were in one of the science fiction series, and I can't think of it off the top of my head right now, but it's the typical drive, right? We may prove that eventually, and once we get the ability to go FTL, that if we put a person in a ship that goes faster than light, they completely deatomize. Well, then we can prove this, right? Hopefully we test it with non-living matter first, but let's just say we didn't, and we send somebody, and all of a sudden they deatomize. Well, then we can prove no material object can travel faster than light. But we can't prove it right now because we can't even travel as fast as light at this point. Right? We limit with traveling, quantities of sound, let alone light. Even if it was supported by 1,000 other experiments, this hypothesis could not be proven by a single experiment. So we can't prove it. We have no way of proving it wrong, right? So here's some more scientific hypothesis, right? The alignment of the planets in the sky determines the best time for making decisions, right? It can't be proven wrong, nor can it be proven right. It's speculation, right? I made really good decisions this month because Mars is in transit and Venus is in retrograde. Really? Intelligent life exists somewhere out there in the universe. It can be proven correct if we come across it, but then we have no way of proving it wrong if no life is ever found. Right now, just saying that isn't necessarily a scientific fact or a hypothesis, right? Because right now, if we don't find life on Mars, well, we can say, well, we just didn't find it on Mars, so it must be on Mercury. Well, we go to Mercury. Well, it's not on Mercury. It must be on Venus. Well, it's not on Venus. Well, it must be on Pluto, right? And we get all the way out, and we're like, well, it must be on Alpha Centauri. Right now, we can't prove it wrong, right? Because it'll just keep going. Well, it might be here. It might be there. It would be hypothetical to say that intelligent life exists on Mars. That we can prove wrong because we don't have any, well, I mean, yeah, we're not even going to get into the ancient aliens whole thing, but I mean, at this point, we can prove it wrong if we go there and there's no intelligent life, right? Alpha Centauri, there's intelligent life in Alpha Centauri. Well, we can't prove that wrong because we'll never get to Alpha Centauri anytime soon, right? I forget how many million light years away, and it would take us longer than many human life cycles to get there. Most people stop for red lights. Doesn't link up with our general understanding of nature, so it doesn't fit into science, right? We understand that Some people think that green light means go, red light means go faster. So experiments are often conducted to test these scientific hypotheses, right? It has to do with discovering facts, relationships between observable phenomena in nature, and with establishing theories that organize and make sense of these facts and relationship. Then we have technology. Technology is our tools, techniques, and procedures for putting these findings of science to use, right? We thought one time that copper conducts electricity, right? And by finding that copper conducts electricity, we then realized, well, most metals conduct electricity. We were able to find better metals to conduct electricity. And then we were able to find out that, well, maybe fiber optics can transmit light. And we were able to get great things like that. So all of this helps us with further tools and techniques. And as technology evolves, science evolves. And as science evolves, technology evolves. So they make a large part of our everyday life. And they make it up every day larger and larger, right? Scientific way of thinking becomes vital to society as new facts are discovered and new ideas for caring for the planet are needed. We are in an environmental crisis of phenomenal proportions right now. Whether you believe in climate change or you don't believe in climate change, we are at a tipping point in science, right? If we don't start researching further how to stop greenhouse gases and how to reduce our emissions, you know, in the span of maybe even my lifetime, or definitely your lifetimes, because, you know, y'all aren't old like me, there's a good chance we don't have Miami anymore, because Miami is now 3 feet underwater. And it actually is happening. If you down to Miami during high tide, that water is coming up onto the roadways. I remember going back there when I was a kid, because I remember going to Miami, probably my earliest time was, I think, 18. There was no water up on the roadways. So in the short period of my life, climate has changed that much, right? What happens tomorrow, going back to that intelligent life thing, what happens tomorrow if the government suddenly admits, yeah, we've been talking to aliens this whole time? That's going to fundamentally change the way science works, right? So we have to understand that science is going to have to ever evolve. So science is mostly concerned with discovering and recording natural phenomena. Then we have the arts, right? They're concerned with the value of human interactions that pertain to senses. The arts are very, very, very emotional for most people, right? Think about if you're thinking about your favorite song ever, right? You've got that evokes a feeling in you, right? A sad song, you listen to a really sad song, it evokes a feeling in you. You watch a really sad movie, it evokes an emotion. Science usually doesn't do that, right? It's just, it is or it isn't. And then religion's considered with the source, purpose, and meaning everything. And I'm going to get on my soapbox here a little bit. Please don't say this, but I really think that religion and science are linked a lot closer than you think. Personal opinion, not scientific opinion, not opinion of Pima. I want to get that stressed out there, that I think religion is formed by the basis that we don't understand things, right? Why was the first religions developed way back when we were, you know, building huts and herders and gatherers? We developed a religion because we didn't know where the sun went at night. And we were worried about the sun coming back. The Aztecs are a great example of it, and so are the Mayans, right? They sacrificed people's hearts in order to get the sun to come back the next day. Now, we know nowadays that that just seems silly, right? What would happen today if somebody came out and said, I've got a way to stop greenhouse gas? All we have to do is build a pyramid, or actually go to the top of the Washington Monument, and all we have to do is throw 500 babies off of that Washington Monument every day, and we'll stop global warming. But that was the religion back then, right? So religion evolves as well, as much as science does. You know, you guys will find out quickly that I was raised Roman Catholic, and the Pope that we currently have under the Roman Catholic Church, I am no longer Roman Catholic, but the Pope that we currently have under the Roman Catholic Church is probably the most scientific Pope we've ever had. I say the Catholic Church, not me personally, right? Or we as a people. But when you look at some of the greatest discoveries in science, I don't know how much you guys know, down in Tucson, there's an observatory, right, run by the University of Arizona. That observatory is funded by the Catholic Church. The Catholic Church funds, I can't even tell you, I think it's 15 scientific observatories across the world. I don't know if it's 15, it's a bunch. Don't quote me on that, please. That's not a scientific fact. But I could perform a hypothesis and prove it wrong or right. So the domains of science, art, and religion are different, but they do overlap, right? The domain of order and natural order is science. The domain of religion and purpose is often considered as religion, but I mean, to some people, science is a religion. If you ask Neil deGrasse Tyson, he'd probably tell you that science is his religion, right? Definitely Bill Nye, stuff like that. But if you ask certain followers of religion, they're definitely anti-science, and never has that been more right in the world. I'm just looking nowadays. So the principal values of science and the art are comparable, right? Literature describes a human experience. The arts don't necessarily give us experience, but they describe them to us. They can evoke an experience in us. They can evoke what may be in store for us. Never would I have thought that I'm living in a world where 1984 is a potential, future plan. But looking where we are today, I mean, it's not that far off. I hate to say it, right? Animal Farm. Those are all literary experiences, but we just haven't learned from our past. Science tells us what's possible in nature, right? It's possible, it helped to predict possibilities in nature even before these possibilities have been experienced. We can predict that the oceans are going to rise to dangerous levels. There's just a article out a few months ago, I think it was in Nature or Science Weekly or one of those magazines, that showed that eventually there will be a great northern push of population, meaning that the population is going to move from even the middle areas where we are now, because it's going to become inhospitable to human life, to move north to areas like the Dakotas and Montana and stuff like that. Because eventually this area here, I mean, just think about it. If it gets to where our summer days are 155 degrees outside, that's not compatible with human life. And so we're going to have to look at it. We can't even cool. I mean, think of it. How many of you guys lived here for a long period of time? When I started living here back, 10, 11 years ago, my air conditioner was able to keep up. Nowadays, on hot summer days, I'm lucky to keep my house at a reasonable temperature, because the temperature outside is just that ridiculous. How many days have we seen over 130 degrees in the Southwest recently? Progress in our age is much quicker than it was 1,000 years ago, but I think we've hit kind of a slump right now, right? If you look at the way we progressed, we had the Industrial Revolution and it kind of dropped. And then we had the digital revolution, right? Through the 90s, where computers became mainstream, right? I've got 4 real computers sitting around me, plus technically, I mean, I'd say the phone's a computer. So 5 computers sitting around me right now. I've got my desktop, I got my 2 laptops, and I've got a tablet sitting beside me. Years ago, that would have been ridiculous, right? My very first computer I built, I remember, was just this huge honking thing, right? And it was a DX33 computer, barely did much else than show pretty pixels on the screen, right? DOS based. Nowadays, our computers double. I mean, I was just sitting here a few minutes ago watching television on my computer. If you'd have told me that 20 years ago, I'd have been like, nah, that's not happening, right? Well, we've kind of hit this plateau, and it's, I'm a big computer gaming geek, and we kind of hit a plateau in computer gaming, right? Every so often, we take these big jumps in gaming, and we just hit another jump. I don't even want to go into that. But I've had the same gaming desktop now for 5 years. Does it run everything at top-notch bells and whistles? No, but it runs it effectively enough that I can use it. That didn't used to happen. We used to have to upgrade literally every 9 months, 12 months. So we kind of hit a slag down. Now, does that mean that things aren't going to change? No, I think the next big jump potentially could be AI. And unfortunately, that brings on the whole idea of Skynet and all that fun stuff as well, right? Oh, I went past. So, when we look at stuff, the pyramids, how did we build them? Right? They're a testament to human genius, endurance, and thirst for deeper understanding. But the pyramids, Machu Picchu down in South America, the pyramids in Thailand, even the ones like Tulum and Chichen Itza down in Mexico. if you ask modern builders, even they would say that there's no way to build these without modern machinery. But we did them, right? We moved from pyramids, these beautiful cathedrals, synagogues, and temples, right? Because we were trying to show the gods that we worshiped them and they were great. And it also was to bring people together and get money. But that's not the point, right? The enormous amount of human energy is focused on a vision that went beyond world's concerns, the concerns of the cosmos. What was out there, right? Today, some of our most skilled scientists, engineers, and artists are directed toward building spaceships that orbit the Earth, right? We have the space station right now that is over us, flying in the space, and there are people living up there, right? They just had a great discovery this weekend that showed that there is water on the moon. Do you know how big that is? Because they believe it's fresh water, where we're starting to run a little low on fresh water, aren't we? Salt water we've got. We haven't come up with a way to desalinate water yet that's effective. But there's maybe fresh water on the moon. That could be huge down the lines, right? You know, where will your kids end up, right? Today, many people working on today's spaceships were alive before the jetliner carried passengers, right? I remember, I'll never forget my first trip overseas. That was back, again, I was an exchange student. That was way back when. But man, back then, the chairs in the airplanes were comfortable. Lots of space. Now we're like crammed in like sardines, right? But now we can take hundreds of people across country in what, 8 hours? How long did it take Lewis and Clark to get across the country, right? Where will our kids end up? And I'm saying our kids, I'm mainly meaning your kids, because I don't think this world's ready for kids for me, right? But will they be traveling to space? Will they be the first ones that colonize Mars, right? Will they be the first ones that colonize the belt and lead us to an expanse-like population? If you don't get a chance, if you have never gotten a chance, the Expanse, great series. Definitely better books, but the Expanse series is pretty good too. Highly recommend. Amazon Prime, watch it. So force, right? And this isn't may the force be with you. These are not the droids you're looking for, right? But force are things that cause changes, right? When things are in balance with one another, we talk about equilibrium, right? We talk about in a human body, homeostasis is an equilibrium, right? Things in mechanical equilibrium are stable without changes in motion. Right now, my phone is laying on my desk. If I put my hand on it, I'm exerting force on it. But if it just rests there, it's in mechanical equilibrium. It's just sitting there. It's not doing anything. I can build piles up, right? We go out to the red rock. The rocks out there are in mechanical equilibrium. They're not moving. Can they change? Yeah, if a force is enacted upon them, it changes them from that resting stage, right? A force is needed to change an object's state of motion. When you are in bed, a force is needed to change you, to get you out of bed. Usually that force is your alarm clock, right? Or your spouse kicking you in the bottom, telling you got to get up, you've got blah, blah, blah to do today, right? Sometimes a great force is needed. Sometimes the force is just needed to move your hand over and hit the snooze button. And force is needed to change an object's state of motion. Force can be a push or a pull. It's always required to change the state of motion of an object, right? The combined of all forces acting upon an object is called the net force. The net force of an object changes its motion. The unit of force is the Newton, right? So for those of you who don't know, when Fig's design, Fig Newtons were designed, those little delicious little cookie cakey things were designed, they came up with the idea of force. No, they didn't actually. This came from Sir Isaac Newton, right? And Sir Isaac Newton didn't get, that's not what the Newtons were named for, right? But he came up with the idea of force. He developed a lot of our laws, and we're going to talk about those as we go through this. But let's say that, we're in the clinic and we have to move a patient around the room. If the patient is very heavy, it may take multiple of us to push that bed around with that patient in it. That means there would be multiple forces acting on the object. The sum of those forces would be a net force, right? The sum of the net force could just be me, right? I've got my phone here, right? My phone's got a good case on it. Down it goes, right? What force is it acting upon my phone here that's causing that to happen? Well, gravity, right? Now my phone's in my palm. Gravity is still pulling it down, right? But the muscles in my arm are resisting that downward pull of gravity and going up. So right now the net force on this phone is 0. It is in equilibrium because it's not moving. Well, I'm moving, but you get my point, right? There's a force pulling down, there's force pushing up. It's just sitting there, right? Now, if I, for whatever reason, change my force, it drops, right? Or if I push it up, right, I increase the force, that's going to change the net force. So here we have kind of the idea of the net force is acting upon a thing. So in the first one here, we have a 5 Newton force pushing to the right. We have 10 Newton force pushing to the right. That's going to result in a net force of 15 Newtons to the right. In the middle, we have 5 Newtons going left, 10 Newtons going right. It's going to result in a 5 Newton force going right. In the case of the bottom one, we've got 5 Newtons going both ways. Well, because those forces are equal and opposite of each other, the net force will be 0, and that object will then be set as being in equilibrium. There's still forces acting upon that object, but the sum of those forces is 0, so it's not moving. So I just talked about holding a rock, book, ball, phone, whatever it may be, right? We're resisting it. Because the object is being stable, the net force acting on it is 0. So let me get a book here. So I've got Essentials of Musculoskeletal Care here. Oh, huge book, right? As I hold it here, gravity is pushing down, right? I can feel gravity pushing down into my hand. And you can see my hand kind of shaking a little bit because this is my weak hand. But as gravity's pushing down, I'm pushing back up. I can increase my resistance against gravity by moving the book, right? I can decrease it by letting gravity pull me down. But if it's just sitting here like this, the net force acting upon this book is 0 because I'm pushing up, it's pushing down, the book stays where it's at. So on the bottom here, if you're holding a 1 kilogram book, you're required to exert a force back upwards to resist the gravitational pull downwards, right? Depending on how we are, right? Typically when we lift things kind of like this in a curl motion. Most of the time those forces are resisted by the biceps brachii. I can lock out my biceps brachii and try to lift the book just with my wrist flexors. That's a whole heck of a lot harder, right? That's a ton harder than lifting with my big old 2-headed monster of biceps. So tension, right? A stretch spring is under a constant stretching force called tension. The pounds Newton's forces are used unit of weight, right? And we'll talk about kilograms being a unit of mass, which we'll talk about later, not right now. So we have this unit of force. Newtons are our key unit of force that we're going to deal with, right? So whenever you have a problem in my class, and we're going to get some problems, not this lesson, starting next lesson, so don't freak out yet, where I may ask you to calculate the Newtons of force pushing down on this book. Well, before you can do that, you have to know the weight of this book, and you have to be able to convert it from either pounds, or if it's in grams, convert it back to grams or kilograms, right? Because remember that for every 2.2 pounds, that equals 1 kilogram. So remember that good old conversion. So if we have some strings holding bags of sugar, right? So we have strings holding bags of sugar here. Let me get up in the little drawing tools, right? So we got a bag of sugar here, right? Well, that's a little bag, right? And we're going to say that the bag weighs about 2 pounds. Well, 2 pounds is just about 1 kilo. It's a little short of 1 kilo. And you're going to find soon in one of the future slides here that the force pulling stuff to Earth is pulling it at 10 newtons per kilo. We'll talk about this in a bit, right? So this is 2 pounds. So this example is saying that this bag is being pulled to Earth with 9 newtons of force, right? If we put a spring around it here, or string, whatever you want to call it, if the bag stays at a constant location, then that means this spring or string is pulling upwards with equal amounts of force. What would need to happen in order for it to move upwards? Well, the force pull upward has to be greater than 9 newtons force. What would cause it to sag further down? Well, if it was going to sag further down, then the string or spring would have to not be able to resist that full 9 newtons of force. So gravity is going to overtake it until it encounters something that it can't overcome, right? So in this case here, there are two forces acting upon the sugar, the tension force acting up, the weight acting down. If they're both equal, right? If those forces are both equal and there's a 0 Newton force, then that means that object is not going to move at all. It's going to be stuck where it's at. And that we'll talk about is going to be called as being an equilibrium. So force vectors. When we talk about force vectors, we're going to talk about vectors a little bit more towards the end of this. A vector is an arrow that represents the magnitude and direction of force, right? A vector quantity needs both magnitude and direction. So force is therefore an example of vector quantity. Scalar, and you're going to see, I'm going to beat this into you because the difference between force or vectors and scalars are important. Scalar quantity described as a magnitude only and has no direction. Time, area, and volume are scalar quantities. The weight of this book, just the mass of this book, is 3.25 kilograms. That is a scalar. The force being pulled down, right, 3.25 kilograms, and it's pulled down at 10 newtons per kilogram, so 32.5 newtons down is the pull that's happening. That would be a vector because it has a direction. If you're, you start a run and you go running out of your front door, we can get your instantaneous speed, how fast you're going. But in order to have that change from a scalar speed quantity to a vector, we'd have to know that you're running a certain direction. So maybe 5 miles an hour north. So in the case here, this arrow, right, it represents a force of 60 newtons to the right. So scalars, right, are quantities. Vectors are quantity numbers with direction. So here, you come to school or drive to work. You could be driving 65 miles an hour. That would be a scalar. And we'll discuss later on about being instantaneous speed versus acceleration speed and stuff like that. That's not important right now. But you look down at your speedometer. Your speedometer says 65 miles per hour. That's a scalar. Now you get on I-15 and you're going north. Now you're going 65 miles an hour directly north. You have a scalar and a direction, so therefore it becomes a vector. What that means is you can change the object's state of motion by either changing the force applied to it, the speed in this case, or the direction it's going. Go from north to west. That would change the object's state of motion. The equilibrium rule, which I've been talking about, right? We can state that the equilibrium rule mathematically says the net sum of all forces acting on an object is 0, then that object is in equilibrium, right? The symbol, that little kind of weird looking E, is the sum of all forces, right? Not the sum of all fears. That's a Tom Clancy book or a movie, whichever you want to call it, but the book was by far better, right? In physics, the capital F stands for force, right? We're going to learn a little bit. One of Newton's laws, force equals mass times acceleration, right? Capital F stands for force. So what it's saying here is if the sum of all forces acting upon this book equals 0, 32 newtons down, 32 newtons up, it's not moving, therefore it is in mechanical equilibrium. It has a sum of all forces being 0. It's a state where no physical changes occur. So for suspended object at rest, the forces acting upon the object must be balanced by forces acting downward. So if I grab a hold of this book on either side with my fingertips, again, 32 newtons of force pulling down. I'm just going to keep using this because I've already measured the weight of this book. At each of my index fingers right now, oh, that's going to tip. Let me get it to a point where it's not tippy. There we go. Whoop, 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 balance. Once I get it in balance, there we go. I got it in balance now on my fingertips. At that point, my fingertips are pulling upwards with 32 newtons of force, right? Along with the rest of my arms acting in coordination with it, right? Gravity is pulling down with 32 newtons of force. The book is not moving, therefore it's suspended at equilibrium, right? The vector sum equals 0. So with that book again, right? So I've got, let me get over here where I can draw. The book's being pulled up with 32 newtons of force. Or it's being pushed up, all right? That's me, by me. It's being pulled down with 32 newtons of force. And that's gravity. Therefore, both those add together, 32 up and 32 down. The overall effect of that is a net force is 0, right? But let's take a look at something here. Let's say instead I put it on my pinkies. Maybe this is gonna be rough. All right, so I don't know if I can pick it up with my pinkies. Let's see. All right, so I'm starting to pull it up with my pinkies. I've got a little bit of support here as I'm pulling it up. Eventually, my pinkies are gonna fatigue, and I can feel it happening in my left pinky already, right? At that point, I'm starting to not be able to hold 32 newtons of force. So what's gonna happen to the book? Gravity is going to take over and it's going to drop to my desk. And I don't want to drop to my desk because I don't want to make a loud boom, right? So at that point, then it would leave equilibrium. So here we have the book again, put on a scale. So the scale doesn't show it, but it does say 32.25 kilograms. You can't see it. So here I'm holding it out on my arm, right? Force upward is equal to the force of gravity pulling down, right? So it's pulling down at 32 newtons, it's pushing up at 32 newtons. The object is in equilibrium. So bridges are excellent examples of things that should be in mechanical equilibrium, right? They're designed with the structural maximal weight. So the structural engineers have to consider what would happen if that bridge is loaded with, say, tractor trailer trucks. Could it support that? Bridges are typically always over-calculated and over-structurally designed so that it's more than can ever appear on this bridge, right? Let's say tomorrow we find out that transformers are real. And, you know, not only transformers are real, but super huge megazoids from Power Rangers are real. And they go stand on the average ordinary bridge here in Las Vegas going over the 15. More than likely, that bridge is not going to be able to support its force because it wasn't designed for that, and the bridge is going to collapse. Right? So if the structural support of the bridge is not able to exert an upward force equal to or greater than the amount of gravitational pull downward, the bridge is going to collapse. Look at this bridge here to the left on this picture, man. This thing looks like it's definitely a mechanical equilibrium, right? You'd go across that in a heartbeat. No, that looks like some bridge in Indiana Jones or something to that effect. That's just saying, I'm going to break your ankle somewhere along here and you're going to fall to your death, right? But this is important because if you think about it, you know, most of our bridges that are out there, especially the large bridges that cross rivers and lakes and whatever else it crosses, most of those bridges were designed in the 70s, maybe 80s, maybe 60s sometimes, right? And if you actually knew how bad the bridges were, you know, how bad our infrastructure is nowadays, I don't know that you drive on them, right? We had a big bridge back where I'm from, back in the East Coast, called the Bay Bridge. The Bay Bridge crosses over the Chesapeake Bay. It's a huge suspension bridge, and it's terrifying. I hated going over it. Like, my object when I got on the Bay Bridge was to see how fast I could get to the other side, not because it was cool, but because I didn't trust the bridge ever, right? But how often do you think they inspect that? I don't think they inspect it as often as you think they would, right? They just didn't. There was a whole study I think it was in 2016, because it was about when President Trump was elected into office, that showed that something like 70% of our bridges in the United States are in disrepair, right? And something like 25% of all bridges are structurally unsafe at this point. That's terrifying, right? When you think about it, I know, because we had some bridges back in Pennsylvania that were a total sketch, right? That bridge is sus, needs to vote out. Because, you know, the bridges were nothing more than planks and plywood, but we considered them safe back then. We don't consider them safe anymore, that's for sure. I saw one of them going back to where my uncle lives. Literally, it goes across the creek, and all my uncle does is every now and then go out and throw some new planks on the bridge. Right? That's not exactly, I don't know, I wouldn't exactly call that safe, right? His idea is, well, if you end up in the creek, you just drive through the creek. Well, yeah, you've got a brodozer, Uncle Lyle. I don't have that. I was driving a rental car. So let's say you're hanging from Olympic rings, right? And those rings are purely vertical. If your rings are purely vertical, your weight is going to be equally supported between those two rings. So if you weigh 100 pounds, each of those rings would be resisting 50 pounds each of your weight being pulled down. If those angles change and now your rings come in at 45s, or maybe one of them comes in at a 45 and one of them straight up and down, those actual functional weights will change, right? And the amount that's being resisted may be problematic. Maybe one of those rings, you know, if you have one over here that's not resisting as much, and now this one's got more of its force, that may exceed its force resistance, and they may cause catastrophic failures. There's whole things and theories about that with, I don't know if you guys have ever seen the American Ninja Warrior, right? They have those things they have to go across. That's just looking at force vectors. How you get across those rings or all the things to climb across and stuff like that. It's just looking at force vectors. There's scientific ways to do that, all of those devices. Even if you're not the strongest, best shaped person, there are scientific ways you can overcome every single one of those obstacles. I'm not going to do it, but. So support force. For an object at rest on a horizontal surface, the support force must be equal to the object's weight. Right now, my book is at rest on my desk that I was holding up, right? The book is pulling down 32 newtons. The desk is pushing up at 32 newtons. The support force then is just resisting this book from going down, right? One force is due to gravity, the weight of the book. The other force is the force acting up, resisting gravity, right? That upward force balances the weight of the object, and it's called the support force. Every desk has a recommended support force. Every chair has a recommended support force. And we're going to talk about that when we get into wheelchairs. The standard everyday ordinary wheelchair has a normative support force of 250 pounds, or a little over 115 kilograms. That means that that sling that's in that seat, that sling, you know, leather seat, can hold upwards about 250 pounds. Now it can do a little bit more than that. Usually they're rated at 250, so it's about 260, 270 that it can resist. But if you get much more than that, the actual stitches in the sides will come out and that seat will collapse, right? I'll see if I have a great picture of that somewhere. I had one of those comfortable chairs that you could sit in, you know, the folding out chairs are great. And somebody replaced my chair with one that they had cut the backs off of at a car show once. And I sat down in it and the support force was no longer there. I ended up down on my butt inside the chair, and it took like 3 people to get me out, and they thought it was hilarious, and I've never been more angry, right? But that support force is often called the normal force. So support force is what's keeping an object at rest on a surface, and it's also known as a normal force. Again, this first lesson, a lot of definitions. Just read through it. So here we have that same book as before. We've already determined the force pulling it down is 32.5 newtons. That means the desk, and also that scale, because technically the scale is enacting a force as well, right? Because if it didn't, that scale would be crushed. But the scale is enacting force upwards as well, right? Of about 32.5 newtons. Now, with that scale in the book, by adding that scale under the book, we've changed the weight acting upon the desk. Because now the desk is not only resisting the book, but it's also resisting the weight of the scale. And we can keep piling stuff up and piling stuff up and piling stuff up until we can determine what the actual support force of this desk is. And that's what engineers will do when they're designing furniture. They're going to keep piling weights on until they know where that structural integrity of that desk is no longer valid, right? The middle of your desk is usually the weakest point. If you have nothing, if you have no support joists between the desk, right? My desk itself, I have 2 kind of side sections, but there's literally nothing in the middle. Whoever designed this desk didn't design it very well. So there's no support joist between them. In the middle of my desk is where my monitor mount is. Well, when I put that monitor mount at first on here, the desk went like this, because I've got 3 huge monitors attached to it. So I had to actually go in and reinforce my desk by putting a cross joist in order to provide that with enough structural rigidity in order to hold up my monitors without bowing, right? And not like Boeing 747, like bowing is in forming kind of a U shape, right? So support force is always positive and the downward force is always negative when we're talking about gravitational forces. So whenever we talk about a gravitational force pulling down, that force is always considered a negative force because it is going down, right? And you can think of it that way. If you're going down, you're going negative, right? When you stand up for yourself, you're going positive. when we have a normal force or support force, the forces acting upon the object is always going to be zero. Therefore, that book is going to be in equilibrium. So the book itself, lying on the table, atoms are being compressed. They're squeezing, right, on the book. They're squeezing down, squeezing, squeezing, squeezing. And the atoms of the desk are squeezing up and up and up. And so they're causing that kind of force. So if you're standing on a balance beam, how much force must the balance beam exert on you in order not to sag? Well, it has to exert at least the same amount of force as your body is coming down. Now, for whatever reason, that force, that beam suddenly decides to exert greater than your body weight, it's going to throw you up. Think of the idea of a trampoline, right? If you just walk in on a trampoline and stand on it and get balance, it's just going to sit there, right? You start jumping on it. What happens is your force coming down starts causing that elasticity of that trampoline. There we go. I lost my train of thought there. To change, and therefore the net force, the support force, actually becomes greater than what gravity is acting down, and it throws you up into the air, right? And you all giggle, and most people fall and break bones, or at least that's just my theory when I'm on a trampoline, right? So what happened if you balance yourself perfectly between two scales, right? So you take out a scale. Obviously, this scale here is not going to support my weight because it's only good for about 25 pounds, and if I weigh 25 pounds, I'd be directly lying, right? But so you put a scale down on the floor, put another scale down right beside it, and you split your weight evenly amongst those scales. What would happen? Well, each scale is going to read about half your weight because you're splitting your weight evenly amongst those two scales. If you push one of them further out to the side, then your weight distribution is going to change. Well, how can this be useful for PT? Right? Well, if you're given a weight-bearing status, which happens quite frequently, maybe a patient damaged their knee, so they got a ACL tear. The doctor may order that the patient's only a 10% weight-bearing status on that lower extremity. So if they're 10%, you have to be able to express to the patient how much is 10%, because they don't understand that. You tell a patient 10%, they don't got it. So you get one of these good old scales out, right? You put it on the floor, and you know that they weigh 100 kilos. Well, you know that 10% of 100 kilos is 10 kilos. So you have them put their foot on a scale until that scale lights up to 10 kilos. And you're like, that's how much force you're allowed to put down on that foot. It gives them the ability to understand how much support force they're allowed to put on that foot. Physics of physical therapy. Dynamic equilibrium. Well, if we have an object at rest equilibrium, static equilibrium, then we also have to have a dynamic equilibrium. This is when objects are moving at a constant speed in a straight line path in a straight direction, right? That would be considered dynamic equilibrium. So here's a quick question. When you drove to school today, did you drive the whole way in dynamic equilibrium? Well, no. You didn't drive to school today anyway. Well, you drive to school later, I guess, or whenever you read this, it might be different. Anyway, whenever you drive somewhere, are you in dynamic equilibrium? You can be for certain periods of your drive, but you're constantly changing speed and changing direction, so therefore you're not in dynamic equilibrium. Let's say instead we get out to space and we throw a baseball, right? Space is a vacuum. There's no other forces acting upon objects out there in space until you encounter some other object, right? And you get that baseball and you get some force behind it and you chuck it. That baseball will forever continue at that same straight line path, forever, at the same speed you sent it off at. That baseball then would be in dynamic equilibrium until it encounters something that it bumps off of, like another planet, asteroid, or an alien's head. So state of rest is only one form of equilibrium. We also have state of rest at direction and speed. That would be dynamic equilibrium. So if the object is moving straight line in the same speed, that means that force is only under the force of movement. Therefore, it's in dynamic equilibrium, right? So if there's no force at all, when two or more forces combine to be zero, that object is considered in equilibrium. So let's say we're pushing a desk across the room floor, and it's got those little sliders on it to help it slide. Once your force pushing on that desk, right, equals the amount of friction that the floor is resisting you with, at that point, the desk will slide across the floor at an unchanging speed. You've overcome friction. If you move it at the same direction, that desk will then be in dynamic equilibrium. If you increase your force to be greater than the friction force, you'll accelerate, you'll go faster. If you decrease the force to less than friction, friction will eventually win. We often say deceleration at that point, but in physics, there is no deceleration. That term doesn't exist. Your desk would negatively accelerate until it comes back to rest. So if you weren't able to resist friction, it'll get harder and harder and harder until that desk just stops. Right? But if it's in dynamic equilibrium, the net forces, the friction acting upon it, the force you're pushing against it, and it's moving in a straight line, it is considered to be in dynamic equilibrium. So when that desk moves at a steady constant speed, without changing its motion, without changing its direction, it's in equilibrium. That friction we talked about is that contact force between two objects, right? Mr. Miyagi's famous trick. Oh, that heat that you feel is caused by the friction of your hands rubbing together, right? You get out in the cold and you're like, oh my God, it's cold. Right? And you rub your hands together. Well, when you breathe in your hands, you're actually countering that idea of rubbing your hands together because you're putting moisture on your hands, reducing friction, right? If you want to increase it just by doing this, don't breathe in your hands because that means the friction force is greater, right? And how do you know that it's getting warmer? Well, you get that erythema and that redness in your hands. So even when an object is moving at a steady speed, where the force moving it is equal to the force of friction resisting it, and it's moving in a steady direction, meaning directly north, directly west, directly to the right, directly to the left, whatever that direction is, the sum of all forces at that point would be zero, and therefore it's in dynamic equilibrium. So an airplane flies horizontal at a constant speed in a straight line. Its state of motion is unchanging, meaning it's not speeding up, it's not slowing down, it's not turning right, it's not turning left. There would be two forces in equilibrium at that point. There are two forces acting on the plane. The thrust of the propellers pushing it forward, or the jet engines, whatever it may be. And the other force is air resistance, which would be the air friction, the air pushing backwards, right? You know, eventually, if you don't provide enough force moving forwards, the plane will slow down. Right? This is why when we launch something into space, it's pretty easy once we get a satellite going around Earth and get it in motion, it will stay perpetually in motion on its own because of the force of gravity and the fact that there's no air resistance in space, right? So which force is greater at that point? Well, if the plane is in a constant speed and a constant direction, neither are. The net of those forces are going to be zero. The positive force of the thrust versus the negative force of the air resistance, they're going to equal out to zero if that plane is in dynamic equilibrium. So when your pilot takes you up to 35,000 feet, you're flying across the United States, getting nice x-rays in your body while you're up there, right? At some point, the pilot will say, we have reached our cruising altitude of 35,000 feet. We are cruising at 350 knots or whatever they're cruising at, and they're heading west. As long as that pilot doesn't touch the rudder, doesn't touch the thrust pedal or anything like that, at that point, when that plane is just cruising along, it's in dynamic equilibrium. When you put your car in cruise control and you're on a flat surface, not going up or not going down, not going left, not going right, just going straight. So you're driving across Montana, basically. Or, you know, Montana, sure, we'll say Montana. How fast can you drive? We're going across, you know, Idaho or Iowa, right? And you got that nice flat cornfield type look going on. Kansas. As you hit that cruise control and that surface is flat, not going up, not going down, not going right, not going left, and you get up to, say, 75 miles an hour, you hit cruise control. At that point, as long as your car is traveling in a straight direction, you're not turning the wheel, you're not going up, you're not going down, you're not going right, left, not left, you're not accelerating, not decelerating, right, or negatively accelerating. At that point, your car is in dynamic equilibrium. Does that mean you are also in dynamic equilibrium? Absolutely, right? Your car is moving you. So you would be in dynamic. Everything in your car will be in dynamic equilibrium, right? How can you prove that it's in equilibrium? If you take a ball, right, you're flying through, you're driving along, you're in cruise control, and you throw that ball up and down, right? If you weren't in dynamic equilibrium, what would happen to that ball? You'd throw it up, and it ended up way back here, right? Because you're growing along. Because everything's in equilibrium, the ball kind of stays where it's at, right? Now, let's say I throw it up and suddenly I stomp on the gas pedal and I change my dynamic equilibrium to be an acceleration. Well, now that ball is going to end up behind me because I have changed my state of acceleration. And at the point that the ball's in the air, nothing's acting upon it. When it's in my hand, and on my hand it's connected to my arm's connected to my butt's connected to the seat of the car, I move with it, right? Even if you do that to yourself, right? You're at the drag strip and you hammer down on the gas pedal. All of a sudden, you're thrown back in your car as your car takes off. You're pulling G's here, right? Until you reach a static point where you're no longer feeling that effect. So what's your vector, Victor? Roger. Never mind. Okay, some of you will get that. Some of you won't. Probably none of you got it. Now that I think about it, you guys are all too young. This is going to make me sad. This makes me kind of laugh when I was thinking about this. I was helping tutor a student last night for Clark County School District, and her birth date was like 2005. And I'm like, oh my God, I'm old. Anyway, it's a totally different thing. That's a different vector. So vectors we talked about are magnitudes with direction, right? Let's talk about your weight. Sometimes you want it to have a vector, right? You want the weight to go down. If you just talk about your base weight, that would be a scalar. So if you're 200 pounds, I wish, that would be a scalar. But if you say that I want to lose 20 pounds, that would be 20 pounds going down. That would be a vector. When we talk about them, we usually construct a parallelogram to determine what the resultant vectors are, right? And we'll talk about this. Don't freak out totally about this. I'm going to make this as simple as I possibly can for you, right? The sum of two or more vectors is called the resultant vector, right? It's also called the net force if we're talking about force, right? Combining vectors when they're parallel or perpendicular are really easy. If they're in the opposite direction or if they're in the same direction, they add together. So if you have two vectors going right? So if you have two vectors going this way, and one is 1 Newton, one is 2 Newtons, the resultant vector would be a 3 Newton force to the right. If they're opposite of each other. So let's say we have a 1 Newton force going this way and a 2 Newton force going that way. The resultant vector would then end up being a 1 Newton force going that way, because adding or subtracting those together, they're going to cancel each other out. You'll be left with 1 Newton. That's great and all, but what happens in the case of something like this? Where I have a 1 Newton force going this way and 2 Newton force pulling this way, and there's where my object is that we're working on. What's going to happen to that resultant vector? Well, it's going to be kind of skewed towards the heavier force, right? It's going to be going that way. Now, we can do all kinds of fancy math on this, right? We can use parallelogram rule and determine what the actual effect of that force is. I am not going to expect you to do that, right? So let's go on forward here on a slide. Clear this off. So here's that parallelogram rule, right? To find the resultant of non-parallel vectors, we use parallelogram rule, right? We consider those two vectors at right angle to each other. The angle would then be kind of off to the side. We talked about this. So you can calculate this. You can use the Pythagorean theorem, and there's all kinds of other theorems you can use to calculate this. Don't freak out. This is not the rule you are looking for. What I want you to know about this is be able to tell me, I want to change from red. I'm bored of using red. Let's go to purple. Purple is awesome. If I have a 5 Newton force pulling an object, we'll call this north, and I have a 1 Newton force pulling the object east, right? Because you remember, never eat soggy Wheaties, northeast, southwest, right? If I have 5 Newtons that way and a 1 Newton that way, what would be the resultant vector? Well, again, you can calculate this out using math. You can actually calculate out exactly what that resultant vector's force would be. What I would want you to know is that that vector is going to be at the diagonal between them, skewed closer to the greater force, right? And skew means being pulled towards. So let's change this now. So let's say instead, we have forces forming a right angle. Actually, let's just go to arrows because, man, my drawings suck. So I've got one arrow. Oh, well, that was not what I wanted to do. There we go. Now I got an arrow. So I got one arrow going this way. And I got one arrow going this way. And let's say, for funsies sake here, that this arrow is 5 newtons and this arrow is 5 newtons. Is that resultant vector, which is going to be this one over here? Let me change my color so I can get my resultant vector. My resultant vector is going to go this way. Is that resultant vector going to have a skew? No, because the forces pulling on it are the same. It's going to be kind of at the 45 degree, assuming that that angle right there, assuming that this here is a right angle, it's going to have a 45 degree angle vector, right? So it's not going to have a skew. But if I change this and instead make this 6 newtons, it's going to skew to that. Now I change it to 7 newtons. It's going to skew closer to that. Now I make this 100 newtons. That was 1,000. Fine, it's 1,000 newtons. It's going to skew heavily towards that because that's the greater vector force. So I'm not going to ask you in physics to calculate it out. That's not something that we really are going to work too heavily with here in physical therapy. Okay. But it is important to understand this. Why is it important to understand this? Well, let's look at the gastroc, or otherwise known as your calf muscle, right? So your calf muscle, 1, 2, 3. Your calf muscle is also known as your triceps surae, your 3-headed leg muscle, right? Because you have gastroc 1 head, you have gastroc 2 head, and you have your soleus. All of those muscles are going to work to plantar flex or push your toes down so you can come up on your toes, right? That's when you're doing those heel raises at the gym, got weight on your shoulder and like, up on my toes, up on my toes. All those muscles enacting upon that are going to be your gastroc soleus, your 2 gastroc heads, your soleus, also one of your tibialis muscles. We're not even going to go into that, right? Well, why is that important? Well, let's say that you get a tear in this gastroc head. So you've got a tear in that gastroc head now. Does that mean that you can't plantar flex? No, you'll still be able to plantar flex, but the angle of pull is now going to be different. So if we have all 3 of these, and that soleus is a really super strong muscle. It's one of the strongest muscles in your body by volume. The soleus keeps that angle of pull kind of straight up and down. That was a really bad drawing. Good job, Mr. McKeever. Thanks. Right, so that soleus kind of keeps everything in a nice straight up and down line. But now let's just say for whatever reason that gastroc's torn. Well, now your angle of pull is going to change. And it may be more something like that. And so now when you plant down, instead of being a nice motion like this, it may be something like this. And you don't have a nice even pull. That's how these vectors play into effect with physical therapy, especially when we're talking about something like the patellar tendon and having one of our muscles being over dominant over the other, like either one of the quads or looking at maybe the rectus femoris being overpowering over the others, right? It's going to change the angle of pull, and it can lead to things, especially in that knee, like patellofemoral pain syndrome, which we'll talk about later, obviously, when you guys are further along in your career here. But that's where these angles of pull and these vector rules come into play. Is we need to understand that our muscles are designed to pull a very specific way. Our bicep, right? Our bicep is a 2-headed monster that allows us to do elbow flexion. It also helps with certain motions, right? Certain forearm motions as well. But let's just talk about the flexion. Well, the bicep itself is going to be balanced with the brachialis, which is under it, and the brachioradialis, which is out on the side here, to allow for elbow flexion. Right? All of those are going to work in concert so that when I lift up, I'm able to get a nice smooth motion. If I get a Popeye tear, which is what happens when the bicep rips off and rolls up and you get a big Popeye looking thing up here, Well, now I'm relying on my brachioradialis out here and my brachialis, that thin feathery muscle under the biceps brachii, to lift up my arm into this. And so you'll get weird motions as they're pulling up. You know, it's kind of snaking like, almost athetosis like. And it doesn't look normal because now that vector of pull has been changed. And we have to understand that in the physical therapy world, that if we see a change in the way a muscle's pulling or the way that a joint is moving, that it's usually caused by muscular imbalance. And we have to determine what muscular imbalance that is and help strengthen the muscles that are weak and stretch those muscles that are tight. That's the whole idea behind vectors here, right? So let's say we suspended a 10 Newton object midway along a very, very tight guitar string. So we got a guitar string and we put a 10 Newton weight in the middle of it. And let's say we got it on to clothesline poles. Got that hanging there. Is it possible for that string to remain completely horizontal? Not a chance. I mean, I guess if you have a really, really super high tension line, it could, but not a guitar string, right? If you had something like a metal line, I guess it's possible. It's still going to have some sag, right? In order for that 10 Newton load to end up in equilibrium, it's going to have to pull down a little bit until that line reaches a tension force of 10 Newtons upward. And once it does, then it'll sit there evenly, but you'll still have that little sag, right? You can see this when birds land on telephone lines. Our telephone lines have a little bit of a natural sag to them, and that's because of contracting and freezing during winter. We'll talk about that when we get to thermodynamics. But when a bird lands on it, that sag gets greater, right? If you climb up there and sit on that line, which I would highly not recommend, but if you climb up there and sit on that line, that's going to sag further to the point that it may even cause a structural failure, and that line will either break or the telephone poles may break or something to that effect, right? Depending on where you are on that line can affect a different type of sag. But it may reach a point where it's now sagging till it gets that tension that can resist your pull downward of your body weight. At that point, you'd be in equilibrium. So I got a couple of physics review questions here. I'm not going to go through these. These are here for you to review on your own. These are to help you prepare for your quizzes and your tests coming up. I try to put a couple of these in every single physics lessons we cover, just to give you guys kind of a review for what you're going through. So that's it. That's the first lesson. I'm going to stop sharing here. Stop share. That's it. That's the first lesson of physics. That wasn't that bad. I promise. It's not horrible, right? If you have any questions about this, please feel free to message me. I'll be available for any questions you have. If not, I'm going to wish you the best on your A&P class tomorrow. I will be available at any time if you guys need anything. I was available last night. No one signed in. So whatever. Remember, my open lab times again are Tuesday night from about 6 to 7-ish, 7:30-ish, depending on how long I need. And then Fridays as well from about 11 to 2, 3. Last week I was there till 4 because I had a lot of people coming in from the other class. So if you have any questions, feel free to shoot me a message. Otherwise, that be it for this lesson. And I will catch you guys on Monday, I believe, is the next time he has an online class. So I will see you Monday and we'll get back together. By then, you should be able to access your midterm, review it, and then we can talk about if there's any questions. Thanks, guys. Have a good night. I wish you the best. Adios.